Hi, so let's get started. Thank you very much for being here. Our speaker today is Carlee Joe-Wong. She's an associate professor of electrical and computer engineering at CMU. She works on optimization, networking, and also machine learning. I'm really excited to have her here. I've known Carlee for a long time, since grad school. We were actually in the same group together. And she's always been the one that we always looked up to, and we all want to be here in grad school. So I'm really excited to hear what she has to say today. Let's welcome the speaker.
I'm really excited to be here. So today I wanted to talk about some of my recent work on distributed/federated learning. And this is joint work with two of my PhD students, Yu-Hong and Eve, as well as my former PhD student, Jin-Hong, and some of our collaborators at USC and at Google. So the motivation behind all this stuff is that in today's environments, there's a lot of data that's being collected by various sorts of devices. And this data is enabling new data-driven applications. So for example, we have smartphones with all these sorts of applications that are collecting data on our purchasing habits and our web browsing habits and messaging and all sorts of other stuff. We also have things like smart homes, environmental sensors, the Internet of Things, and even medical sensing, again, sort of in the Internet of Things. So we have all this data that's being collected. It has the promise of enabling these new applications. And then the high-level question that many others are trying to ask is, how do we actually make use of all this inherently distributed data? So the fundamental challenge behind all this is that we would like to learn usually a single model or multiple related models across data that's housed at multiple clients. And fundamentally, this requires the clients to exchange information, right? Because there's different data at different clients, so different clients know different things. But there's constraints on how much information you can share. So one of the sources of these constraints is privacy. So in many cases, data cannot be shared across clients. So for example, this is a problem we started talking about with Amazon, which was fraud detection. And in this case, you may have a network of a bunch of users and a bunch of buyers and sellers and potentially products that crosses a lot of different countries. And if you want to do fraud detection, you want to make some sort of anomaly detection and fraud detection model across all this data. But some of this data is very privacy sensitive. So I don't know if you can see here, but some of it is like social security number. Some of it might be sort of highly personal product purchasing behaviors, all that sort of stuff. So there could be some privacy limitations to what you're allowed to share. And this is another example. This is a graph of connections from back in 2010. Obviously, this also could have some privacy implications, your sort of activities on Facebook. And it could also raise some communication constraints. So this is like one user's graph, 14 years ago. Imagine this times a billion, and now you're trying to share this information sort of across the world. That's a lot of data that you have to communicate. So it may be very expensive to share data across clients, even if you're actually allowed to do so. In another setting where communication constraints come into play is when you have learning on very resource-constrained devices. So this is a picture of some low-power featherboards that we bought from my lab a few years ago. So these featherboards, as you can see, they're super tiny, very low power, very limited battery life. So if they're sort of sensing data, you cannot just sort of turn their radios on and tell them like, send all the data you're sensing to a central server at all times. So there's privacy constraints and there's communication constraints. And these are the main challenges that we've been looking at in this research. So obviously, we're not the only ones that have been looking at this problem. And in fact, the whole field of federated learning, to some degree, tries to handle these types of privacy and communication constraints. The basic idea behind federated learning is keep the data at the clients, but have each client sort of locally update some kind of model, typically by using gradient descent. And then occasionally, all the clients send the model to some sort of central server. The server does some aggregation across the clients, again, without seeing the data, just looking at the models. And then the updated model is sent back to the clients, and this process sort of repeats over and over again. And there's many, many variations of this. which try to address various privacy concerns or reduce the amount of communication needed, et cetera. So this framework is great. And it's been shown to be very useful, but in some cases it's not enough. And that's really what I wanted to address in this talk. So one of the fundamental limitations of this kind of federated learning architecture is that you're assuming that clients can learn some kind of local model only based on their data. And the reason I put correlated data in the title of my talk is that this may not always be this. So in this talk, I wanted to talk about two different applications where it's actually not trivial for a client to locally update its model just based on the data it itself can observe. All right, so in typical federated learning, as I said, you have these local updates. Typically, it's just gradient descent. And as I said, there's been lots of work on federated learning, some from our group, a lot from many other groups, which I probably don't have time to cover in this talk. But there's been some work on heterogeneous client updates. There's been some work on personalized learning, where the idea is you try to learn sort of models personalized to each client's data. But this still assumes that clients can compute these gradient descent steps by themselves just based on their own data. Excuse me. And more recently, there's been some work on so-called vertical federated learning, where you sort of partition data in a vertical way across clients. So different clients observe sort of different features of the data. This sort of gets towards the idea of correlated learning, but it typically looks at very rigid partitions of what each client is able to observe, very rigid relationships between what they're able to observe. So in our work, we've been looking at other types of data correlations between clients. And as I said in this work, I'll mostly be talking about two specific applications and how we modified and adapted the federated learning framework to deal with these. So the first is looking at federated subgraph learning. And I'm trying to illustrate what I mean by that here. So imagine you have multiple clients. Maybe these are, let's say, different countries. And each country has a local graph of its own users. And you have some edges between users in the same country, but you also have edges between users in different countries. So in this case, the correlations arise because you have these cross-client edges. So if you're trying to learn a model at, let's say, this client K-1, just based on its local graph, you're going to miss all this information encoded in these cross-client edges. And that's going to compromise the accuracy of your model. The other application we started looking at was environmental monitoring or environmental sensing. And in this case, the correlations are a little less well-defined, but the basic idea is that you have a bunch of sensors. They're collecting data about the same environment, or at least physically correlated environments. And therefore, the data that they've collected has some fundamental physical correlations, which you may or may not know what those look like ahead of time. And then the question is, well, how do we sort of compose all this data that these clients are observing into one model of the physical environment? So these are the two use cases I'll be talking about in this talk. I do think that there's a lot of future work to be done on sort of more general models of this idea of sort of correlated data across different clients. And hopefully I'll have time to talk a little bit about that at the end. All right, so the basic question we're trying to answer is how can federated learning frameworks be modified to handle these sorts of natural correlations? All right, so the first part of the talk will be looking at this federated subgraph learning. So this is work that appeared in NeurIPS last year. Okay, so the motivation here, again, was looking at different clients as different countries. So for example, you may look at social network recommendations, network systems, or cross-country money laundering. So I really like this last example because this is one example where these cross-client edges are very, very important. So you can imagine if you're trying to do some sort of fraud detection, if you ignore all international purchasing transactions, your ability to do fraud detection will be very, very limited. Just because a lot of the times these fraudulent transactions do have international components to them. So you really need some kind of method that can account for these edges that cross these different clients. All right, so Yeah, again, the main challenge here comes from both privacy and communication constraints. The privacy constraints are regulations like GDPR in Europe. India also has some privacy regulations on the data you're allowed to share outside of the country. And the basic consequence of all of these is that you can't just like take information about clients in one country and send all those features to people in another country. All right, so this is the main challenge. So the setup that we're going to assume is, again, we have this big graph where the nodes are partitioned across different clients. Each client knows its own local graph structure. Each node is associated with some set of features. The client knows all the features of the nodes that it contains. And we also make an assumption that clients know about the existence of these cross-client edges. So for example, again, if we're looking at this example from Amazon, where an edge means, I purchased a product from a certain seller, my client is going to know that I purchased a product from that seller, but it won't know any information about the seller. So it knows the presence of these edges, but it doesn't know the features of the node at the other side of this edge. And now if I want to train a node classification model in this setting, typically what I would need to do is I would need to get all of the node features stored in other clients. So for example, if I wanted to classify this green node here, I need to know information about the features of all of its neighboring nodes. And some of those neighboring nodes are in other clients, and this is where the problem arises. So a lot of previous works in this setting have tried to just ignore these cross-client edges, but of course that does lead to information loss. Other works have said, well, we just have to send features across all these clients at each training round. Now this, of course, raises some privacy concerns, and it also can result in a huge communication cost. And there's some techniques for reducing this communication cost, like doing some sort of random sampling or doing some sort of like encryption or differential privacy on the communication that goes between the clients. But still, there's fundamentally a large communication cost and potentially some loss of privacy in communicating this information. So the main message of our work was to look more closely at what these graph neural networks are doing. And what we found is that, in fact, we don't have to exchange information in each training round. It's enough to do this at the very beginning, in one pre-training communication round. And then that helps us both reduce the privacy loss, which I'll explain in a few slides. And of course, it also helps reduce communication, right? Because now instead of communicating information in each round of the training, you're doing one pre-training communication round. And then all the training takes place without any of this cross-client communication. So let me try to explain to you sort of why this is possible and how we were able to do it. And then, yeah, I'll explain how this actually works. So let's consider this very simple input graph. So we have two clients, the blue client and the yellow client. And what I'm going to do is focus on this node here, on node 1. And I want to look at the information that we need to classify node 1. So in graph convolutional networks, this is a typical structure. So I here just means node 1. L+1 means one of the layers of my network. So you typically have multiple layers. So for the L+ first layer, the information I need is going to be this sum here. And this sum, so this is a sum over all of the neighbors of node 1. So in this case, it's on node 1 and then nodes 2 and 3, which are at the other client. And I have maybe some weight attached to the edge between these two different nodes, as well as the features of the node that the previous layer spit out. And then I have the weights of the graph that I'm actually trying to learn, which are these W parameters here. All right, so if you look closely at this sum, what we realized is that this sum over all of the neighbors of node 1, this can actually be pre-communicated because this doesn't change in the actual learning process. All that's being changed is these W parameters here. So what we were able to do is we were able to say, well, why don't we pre-communicate this sum of features from node 2 and node 3 And if we pre-communicate that to node 1, then node 1 could just sort of reuse this in every round of its training, and we don't have to get any more information from the other client. So that's the basic idea of how this works and why we are able to reduce this to one pre-training communication round. All right, so obviously that can help you reduce communication costs, right? But then we also have these sort of privacy concerns. So it turns out this can also help with privacy. So the first way this helps with privacy is that, remember, we're summing over all the neighbors of a particular node. So if you sum over enough neighbors, then you lose information about specific nodes. It all gets sort of aggregated together. And if you only send that aggregation, that helps with privacy leakage, because this aggregation will naturally sort of help protect you against knowing any information about specific nodes. So this, initially we thought this would be enough, but then we realized, well, there's actually some corner cases where it's not enough. So for example, if each client is sort of pre-communicating to each other client, let's say that, so let's focus on this node 2 here. If node 2 only has one neighbor at client K at this other client, then there's actually no aggregation that's being that will happen if all its neighbors from other clients communicate to node 2. So you do have these corner cases where you don't have enough neighbors at other clients, where the aggregation will not help you with privacy. So one way to solve this is to say, well, in federated learning, we usually have a server, and you may be able to assume the server is trusted. So if we send all these aggregations up to the server, then you're more likely to be aggregating across a larger number of neighbors for each node, and that will help you with privacy. So that was our initial insight. Then we started talking with some collaborators at USC who are basically cryptographers. And what we realized then is that you can actually do even better than that. So we could use homomorphic encryption to actually do this summing across all neighbors of each node. So you can do this, generally speaking, in federated learning, right? The challenge is that homomorphic encryption is very, very expensive. So if you're communicating information and aggregating information in every single training round, you're going to increase your training overhead by orders of magnitude. In our case, though, because we've reduced all the communication to one pre-training round, it's actually not that much more expensive to do homomorphic encryption. So typically, homomorphic encryption will add like a 10x overhead to your training. So doing a 10x overhead for one communication round is much better than a 10x overhead for maybe 1,000 communication rounds. So we were able to even to layer this fully homomorphic encryption technique on top of our neighbor aggregation, which finally convinced the reviewers that our solution does in fact preserve privacy. So that's the basic idea of this federated graph training algorithm. And we developed these 3 variations of this algorithm. So the first variation is something that other papers typically did, which was you don't have any cross-client communication. You only look at information in each local client. The second variation is you communicate feature aggregations of your one-hop neighbors, meaning of your immediate neighbors of other clients. And then we also looked at 2-hop communication, where you communicate aggregations of 2-hop neighbors so neighbors that are up to 2 hops away from you and potentially at other clients. And you can sort of go even further with this. We decided to stop at 2 hops for reasons that I'll talk about on the next slide. The more hops away you go, sort of the more communication is necessary. So there are some trade-offs here between communicating features of nodes that are further away and reducing your communication costs. All right, so why did we decide to stop at 2 hops? Well, we actually realized that for a lot of graphs, 2 hops is sufficient. So we did some tests looking at graph convolutional networks with multiple layers and looking at multiple hops, communicating across multiple hops. And what we saw is that in simple graphs, so So this is a graph on Core, which is a relatively small data set. You can see that as we get to deeper and deeper graph convolutional networks, our test accuracy is actually dropping. So it's enough to look at very shallow networks. And even in this OGB and archive data set, which is a much larger graph, much more complicated graph, going to more layers doesn't really help. And going to more hops also doesn't really help your test accuracy much. Yeah.
Is this still in the pre-training stage?
This is actually fully trained. So this is looking at our algorithm after all the training happens.
And the homomorphic encryption is found in the pre-training stage?
Homomorphic encryption is only the pre-training. Yeah.
And even that, the reviewers aren't buying it.
No, once we included homomorphic encryption, then they bought it. Yeah, yeah. But this aggregation stuff, there are corner cases where it doesn't fully protect privacy.
And they're all done in like offline stage, so I guess the computational complexity doesn't matter that much.
Yeah, exactly. So you're only doing this in one pre-training stage. So it's okay if it's 10 times more expensive than it used to be.
Thank you.
I'm not familiar with this data set. Can you say a little bit more about what test accuracy is? What is this network being trained to do?
Oh, sure. Yeah. So here we're looking at a node classification problem. So OGB and archive is a graph where each node is an archive paper, I believe, and the edges between them are common authors on different papers. And I believe what we're trying to do is we're trying to predict the field of the paper.
Oh, okay.
And the idea is, if you co-author a lot of papers with similar authors, then you're probably working in similar fields.
So in that setting, what is a client here? Like, what is the partition?
Yeah, okay, that's a good
question.
question. Yes. So one limitation of this evaluation is that these are all synthetic partitions. I'll talk about that a little bit more later. But I think for this one, we just did some random partitioning according to some distributions. Are there any other questions before I go on?
Since I've already interrupted you, I guess even in the Amazon setting where you had a buyer and a seller, it wasn't clear to me, there's a client there, but that's a consumer client, not a computational client. What is the partition even in that setting?
Yeah, so in that setting, the clients would be different countries.
Countries. Okay,
Yeah.
thank you.
Yeah.
We don't want to share data with each other.
Exactly,
Okay.
exactly.
Despite them all using Amazon.
Yeah, I mean, yeah. Right, all right. So we said, okay, so looking at this limited communication is enough. So if you look at the actual algorithm, I won't get into the details, but basically you first have this communication and aggregation with fully homomorphic encryption in the initial round. And then after that, there's a normal federated training process where each client does gradient descent on its local model, taking into account this feature information that it's gathered in this pre-training stage. That's what enables it to compute all these gradients. And then once the clients have the gradients, they send the gradients up to a server, which aggregates them and updates the model. And then that model gets sent back down to the clients, and et cetera, et cetera, et cetera. All right. Yes, so there is a question about how is this data distributed? So once we came up with this algorithm, one of the questions that I was asking my student was, how important are these cross-client edges anyway? Because for an application like maybe cross-country money laundering, yes, it's very important to look at edges across different countries. For something like, citation networks, does it really matter that much? I mean, if you're looking at the US, for example, right, there's tons of researchers in the US. You can probably learn a decent model just based on, US data. And what we realized is that the number of cross-client edges, and therefore the effectiveness and importance of our algorithm, really depends on the distribution of data across different clients and the distribution of the nodes in the graph across these different clients. So one potential distribution is what we call IID distributed, meaning that every node in the graph is equally likely to be at any other client in the graph. And what this means is that each client has a balanced number of those. You could also look at non-IID distributions. which in this case we were interpreting as saying that each client may have a different distribution of labels. And in particular, you may have sort of concentrations of labels where one client or where nodes of a particular label are concentrated on a particular client. So this is relevant in cases like social networks, where again, the clients are different countries, the nodes are users. And if you're trying to predict, the preferences of a user, the interests of a user, users in the same country may be more likely to have the same preferences. So you'll get these sort of concentrations of labels at different clients. So what this means is that, again, in this graph setting, typically you have an assumption that nodes with the same label are more likely to be connected with each other. That's kind of the basis of all this graph learning. Like you're using your neighbors to predict, you're using the labels that features of your neighbors to predict your particular interests or your particular label. So you have this assumption that I'm more likely to be connected to similar nodes. And what that means is that in this non-IID setting, where these nodes with a particular label are concentrated at different clients, you actually have fewer cross-client edges, which means that ignoring these cross-client edges might actually not be so bad. So this is very non-intuitive for me because I was coming at this from a sort of federated learning mindset. And in federated learning, non-IID data or different kinds of different distributions tends to be very bad. You can actually find examples where federated learning doesn't converge in this setting. But because of this sort of graph structure of our data, we actually found in our setting, non-IID data is good because it reduces the amount of information you have to communicate across clients. So I thought this is interesting. So I asked my students, okay, can you show this theoretically? Like, can you take these convergence analyses of federated learning, apply it to this graph problem, and let's see what the convergence bounds look like. Like, can we actually show that you're more likely to converge with non-IID data? Because that will be very non-intuitive if you come from this from a federated learning perspective. So, there are a lot of steps that went into this, which I don't have time to really talk about too much. But basically what we were able to do is we were able to show this. So the way we were able to do this is we looked at these convergence analyses of federated learning. And what we found is that typically, if you try to get some convergence bound on how accurate your final model is, it will be in terms of some difference between the local model and the global model. And if we make some assumptions about the distribution of nodes in our graph across different clients, we can actually get some expressions for this difference between the local model and the global models. And then if you analyze what these expressions look like, we'll actually see that if you have more non-IID data, so data that is where nodes of a certain label are concentrated at particular clients, you'll actually see that this convergence gets faster or gets better. And if you have more IID data, you'll see this convergence actually can get worse. We were also able to quantify this for both 0-hop, 1-hop, and 2-hop variations of our federated graph training algorithm. And we're actually able to show that we get faster convergence with more communication hops. Again, this is sort of an intuitive thing, but it was nice to be able to theoretically show it. One of the consequences of this as well was that we were able to show that whether or not you actually want to take into account these cross-client edges depend on the number of clients you have too. So if you have a graph that's spread across a large number of clients, you're much more likely to have these edges between clients that you have to take into account. Whereas if you have graphs that are spread across very few clients, each client may actually have enough local information that you can learn a model on that without losing too much in the accuracy of the model or the convergence of the model. So the actual expressions we got, as you can see, they're kind of complicated. But if you actually look at what all these constants mean and take a close look at these, you'll see these sort of high-level intuitions fall out of that, which is pretty cool. So we also looked at some empirical validation. So here, what I'm doing is increasing the number of clients. So on the left graph here, we have 1 to 10 clients, then 0 to 100, and then 100 to 200. And basically what we see is this blue line here is zero hop fed GCN. So this is looking at ignoring the cross client edges. And you see that that greatly reduces the accuracy. And the more hops that we consider, meaning the more cross client information we look at, the better our accuracy is. And as we increase the number of clients, we see a greater and greater difference in the accuracies of 1-hop and 2-hop fed GCN. So some of the sort of intuitions that we saw from our theoretical analysis did actually show up in our experiments here. And again, the distribution of data here, this was a synthetic distribution. So we were able to control the number of clients that we were looking at. In the more extended evaluation, we looked at 4 different data sets. So the first 3, Cora, CiteSeer, and OGB and Archive, these are all citation network data sets. So think of each node being a paper and edges between papers being co-authorship, and you're trying to predict like the field of the paper. The last data set, OGB and products, this was a more marketplace data set, and it was much larger. So you can see it has like 2.5 million nodes and 61 million edges. So that the purpose of that was to just sort of test our algorithm at scale. All right, so this is looking at OGB and Archive. And here what we did is we took our fed GCN variations and we plotted their communication cost versus their test accuracy. And we're comparing that to a bunch of prior work in this area. So DGCN, FedSage Plus, BDS GCN, and of course centralized GCN, which assumes the graph is concentrated at one client. And what we would like to see is lower communication costs and higher accuracy. Obviously, centralized performs the best, right? Because there's no distribution there. But we were able to show that this fed GCN has this order of magnitude reduction in communication compared to these prior works, while also having either comparable or better accuracy, at least in this data set. And the difference between these 3 graphs is how we distributed the nodes across different clients. So as you go to the right, you have data that's more and more non-IID. So you can see that, well, I guess there's not too much of a difference. But for example, looking at this 0-hop fed GCN, where we don't consider this cross-client information, you can see its accuracy increases a little bit as we have more non-IID data, where we have fewer of these cross-client edges. So it's less important to take those into account.
So how is like fed GCN is beating centralized at the right side?
Oh, that's a good question. I think that's just noise. It's not a reliable result.
I see. Oh, I mean, so because sometimes there's this issue of like, what's your evaluation metric? Like whether you are evaluating with local model, like let's say global model, or you are personalizing it to locally.
Yeah.
When you personalize, it might make sense that it's more accurate.
So this is actually the global model. I think the other thing that could be happening is it may be generalizing better. Because with fed GCN, sometimes we're like eliminating some of the cross-client information. So that might also be happening there. Yeah. Okay, I just said this. Yeah, and then if we look at all these data sets, we were able to show that in IID and partially non-IID and very non-IID cases, fed GCN was able to match or even beat at least slightly all these baselines. So all these bolded numbers here are the best result out of all these methods, and you can see they're always fed GCN, either 1-hop or 2-hop. So I wouldn't necessarily say these are super significant improvements in accuracy, but coupled with this order of magnitude reduction in communication, we thought this was a very useful algorithm. All right, so that's most of what I wanted to say about this graph training part of the talk. So to summarize, we showed that cross-client edges affect model performance in this federated graph training setting. And we proposed this algorithm that we called fed-GCN, which helps to recover information on cross-client edges and only requires communication on one pre-training step. That also enables us to use homomorphic encryption to better preserve privacy across the different clients. As I said, this paper appeared sort of in NeurIPS last year. So since then, what we've been trying to do is we've been trying to sort of build out a system that actually helps deploy fed-GCN in practice. So we noticed that one of the barriers to making progress in this space is that when we were evaluating FedGCN, we basically had to collect a bunch of code from a bunch of random papers, make it all work ourselves, and then sort of run all these benchmarks on some data sets that actually ended up being quite large. So the reviewers kept asking for larger data sets, and eventually we had like 16 machines running for one of these OGBM product data sets. So we said, all right, if we really want this field to advance, let's try to make it easier to do these evaluations. So we've been building this Python library, which we call FedGraph, which tries to automate a lot of these things. So far we've basically taken our FedGCN evaluation code and imported it into FedGraph, and we're working on expanding that to other federated graph training methods. Currently, we support node classification models and graph classification models, and hopefully soon link prediction models. We have an undergrad working on that right now. Yeah, our hope is that by building out this library and making it easy for other researchers to kind of evaluate these different methods, we'll be able to first help others really evaluate their new ideas for how to train graph neural networks in a federated way. And second, we're trying to look at benchmarking. What are the actual challenges to getting these things to work in practice? So for example, one of the big challenges we were trying to solve was this communication overhead, but it's not really clear how much communication overhead there actually might be in a real system compared to the computational overhead of actually doing all this local model training. So by having this library, deploying this in a bunch of different settings with different hardware, et cetera, we're hoping to be able to really figure out what are the actual bottlenecks here to deploying these things in practice. All right. So that was all I wanted to say about the graph setting. So the second part of the talk is sort of different application. But again, this similar theme of you have data at different clients, the data has some correlations, and you're trying to sort of do some sort of data fusion across the clients. And this was work that appeared in CCon last year. The motivation behind this work, again, is the Internet of Things. You have a bunch of sensors collecting a bunch of data. You're trying to use this data to learn something. And one of the motivating examples we were looking at here was wildfire tracking. So I used to work at CMU's California campus, and I actually grew up in Los Angeles. So wildfire tracking is something I definitely believe is very important. And that's probably why we started looking at this, because at the time when we started this project, my students were also in California. And the idea behind this is if you want to track wildfires, one way to do that is to scatter a bunch of sensors around an environment, have them collect data about the environment, and then do some sort of data fusion. To say, like, given the wind direction, given the ambient heat, here's where I think the fire is heading. And obviously, this has a lot of practical benefits. So this can enable fire chiefs to collect real-time environmental data to track wildfire spread, maybe issue evacuation warnings, et cetera, deploy resources, all that stuff. So this was sort of the application that we started looking at. And what we realized very quickly is that you can't really just apply federated learning to this because you are sort of trying to learn a model of where the wildfire is going, but it's a very different setting from, every sensor is doing stochastic gradient descent and uploading its results to the server, and then the server is sending back a model. So some of the challenges that we faced in this setting were first resource constraints. So if you imagine sensors being deployed across this sort of wide area, they're typically very low power sensors. So they have very stringent bandwidth constraints, and they also have very stringent battery constraints. So you can't ask these sensors to sort of keep sending you data and having you sort of keep updating some model of where the wildfire is going, which is a problem because now we have to efficiently manage data communication. We have all these different IoT devices. We have to collect data from all of them. We know that they cannot communicate all the time. So somehow we have to coordinate across all these devices without requiring a lot of communication from them. The other challenge, which is also an opportunity, but also a challenge, is spatiotemporal correlation of this data. So if you have these sensors across an environment, the data that they're collecting is definitely going to be correlated, right? Because if you have like wind moving in a certain direction, all the sensors in the path of that wind are going to collect similar data. However, you don't really know what this correlation looks like in practice. So we do know that adjacent nodes are sampling correlated data, but we don't really know what that correlation looks like in practice. The reason I say this is also an opportunity is because we have resource constraints, right, on which sensors are able to transmit data. If you have sensors that you know are collecting correlated data, it may be enough to have only one of them transmit your data. So if you're able to learn these correlations, you could potentially take advantage of them in deciding what information each of the sensors has to share with each other in order to make this model of where the wildfire is. And that brings us to the third challenge, which is how do we define the value of data collected by each IoT sensor in this setting where we have these unknown spatiotemporal correlations. And the fundamental question here is, how do these local observations on each sensor contribute to the global sensing problem, contribute to the accuracy of our model? So when we first started looking at this project, we were thinking of how each observation contributes to the accuracy of the model. And we were thinking, well, if you're using gradient descent to train the model, maybe we could adapt these convergence bounds on how fast the model converges to get a sense of the value of this data. But we quickly realized that this is not sufficient because these sort of gradient descent algorithms don't really take into account these correlations. So instead, we had to come up with another formulation. So the problem, the formalism that we came up with was we would like to maximize the quality of our collected data, again, subject to these resource constraints. So we had to figure out, well, how do we model the quality of the collected data? And then also, how do we solve this problem, again, without requiring a lot of communication between the sensors? All right, so this is sort of the overview of what this paper tries to do. So the short answer to how we did this is we set up a reinforcement learning problem. And we said, well, you can't really communicate between sensors in real time to sort of learn what to do. But you may be able to pre-train the sensors to tell them, here's the policy you should follow. And then if everyone follows that same policy, maybe we can guarantee some sort of good collective outcome. So what we ended up doing is, we used reinforcement learning to train the policy, and then we deployed this policy to all these different sensors so that the sensors could decide what data they should be transmitting at which time. And ultimately, we showed that this led to a more accurate tracking. All right, so how do we actually do that? Here's our system model. So the way we formalize this is we said we have a coordinator that maintains a belief about the system, that is a prediction of where the wildfire is going to go, or this is essentially the model of the environment. And then we have a bunch of IoT sensors here. Each of them maybe is tracking wind, tracking fire, and each of these sensors can make a decision about whether or not to try to communicate with this fusion center. And if the communication is successful, then its data is used to update the belief of the fusion center, that is to update the model that's maintained by this coordinator. And this animation here is showing how we think the fire is going to evolve over time. Because we have very resource-constrained sensors, each communication is associated with the cost and is associated with the probability of successful transmission. And at the fusion center, what happens is you look at the acquired data over time, and as you get more and more data, you sort of update your belief, or you update your model of the system, and that updates what you predict will happen in the future. And then once you see what actually happened and what you predicted would happen, you can define a loss function, which says how accurate was the prediction that you made, given whatever data you were able to collect from your sensors.
And the sensors only communicate with the fusion sensor, not with each other, right?
Yes, that's correct. So the sensors only communicate with the fusion center. All right, so this is sort of the setup of the model. So the problem that the sensors have to solve is figuring out when do I communicate? And what policy should I be following? Right. So yeah, again, in order to decide whether or not to communicate, the sensors need to know something about the value of the data that they possess. So if a sensor thinks it has really valuable data that maybe will meaningfully change future predictions, it probably should communicate that. If the sensor believes, okay, someone else has probably already sent the data that I'm collecting, maybe I shouldn't communicate, I should let others communicate instead. So this is a general idea. Of course, the challenge then is defining the value of the data. And what we ended up doing is we said, well, at least in the offline setting, or at least theoretically, you could compute your error before having the data from the sensor and after having the data from the sensor. And then you could look at the improvement in this error. And if the improvement is large, you say the data is valuable. If it's small, the data is not so valuable. So this definition is based on sort of the Shapley value definitions from game theory. The basic idea is to look at what happens to your error with and without the data from the sensor. So that's our definition of data value. And now that we have this definition of data value, we can formulate our reinforcement learning problem. So we have this value of the data, we have a communication cost, and we can define an objective as maximizing the value of the data minus some communication cost. And we can define a essentially Markov decision process to optimize this objective function. All right. So I don't think I have too much time to get into the details of how we actually model this as a Markov decision process. But basically what happens is the state of each sensor is its observations, its current observations. Its action is just whether or not to send data based on its local observations. And you get some reward that's based on whether or not you successfully communicated and whether or not your communication was able to reduce the error in your prediction. All right, so this is the basic framework that we came up with. And yeah, compared to prior work, yeah, so there's been a lot of work in sort of IoT sensing, which tries to look at sensing from different sensor measurements from different IoT devices and combine them into some sort of prediction or some sort of model. What's interesting is that very few works have actually looked at our particular communication model, where you have a bunch of sensors and they can only communicate with the central server, and they have these very constrained communication constraints. There's also been work in sort of mobile settings where you have sensors that are moving around the environment and you may want to control where they move. In this case, our sensors are sort of fixed. They have a very simple decision to make. Do I send or do I not send? And it turns out that even that is sort of difficult. And yeah, so we ended up using reinforcement learning to learn this communication policy. Compared to other reinforcement learning algorithms, there was no centralized orchestration. We had these communication constraints. And it actually took us a while to figure out how to solve this problem, just because you're so constrained in what policies your agents can execute. There's so little communication that it's actually quite difficult to even figure out, what should this policy look like? What should my state look like at each of these local sensors? And how should we be basing how should we be formulating our local policies? Okay, so for the evaluation, again, we weren't able to collect any real data about this, but we were able to get a wildfire simulator working. So this is a sample of what came out of the simulator. This is based on Yosemite's topography, and we were able to simulate the spread of a wildfire throughout Yosemite. And we also simulated a low power communication network using some path loss models and assuming there's a single gateway, which is a fusion center, and a bunch of sensors sort of scattered around Yosemite. And these examples up here show an example of sort of the true field or true wildfire spread that we were trying to construct, and one reconstructed example. So you can see here, I think this was using some heuristic communication policy. So we were able to construct something that sort of looks like the true field, but obviously it's not entirely accurate. So sort of more quantitatively speaking, so these three algorithms here are our methods where we use various reinforcement learning algorithms to train our environmental sensing policy. We compared them to some random algorithms and also some heuristic algorithms. And here we were looking at first the convergence of our algorithms. So we were able to show they converged, as well as the data value that we achieved, the communication cost, and the error loss, which is the thing you ultimately want to minimize. So you can see that if you look at the random methods, they don't end up sending very valuable data, but they do have very low communication costs. Unfortunately, because these random methods cannot distinguish between the data, the value of the data at different sensors, you end up with a pretty high error loss because you end up sending essentially redundant information or information that's not useful. If you look at our algorithms, you can see we have relatively valuable data that's being sent. We do increase the communication cost a little bit, but because we're able to learn which data is most valuable and most worthy of being sent, we actually end up with much more accurate predictions. So we have very low error loss here.
You see more about what the predictions of the temperature or when the fire will reach a given location? Or what?
Yeah. So the prediction is, when the fire will reach a given location. So we were looking at sort of the difference in time between when it actually reached and when we thought it would reach. Yeah. And then the other thing we tried to measure was we had this objective that's sort of balancing the value of the data and the cost of communication. So we said, well, depending on the scenario, you may want to have different trade-offs between the value of the data and the cost of communication. So here, these blue lines here are our algorithms, the trade-offs they achieved. So the data value is on the x-axis, the energy cost of communication is on the y-axis. And you can see that we sort of kind of span the entire kind of greater frontier of the trade-off between higher communication costs and higher data value. Random, again, has communicates much less valuable data, but sometimes also has a lower communication cost. These two, so this line here, this orange line here, this is actually doing better than our algorithm. So for the same data value, it has lower communication cost. Unfortunately, this algorithm here is the offline optimal algorithm. So this is the algorithm you would use if you could sort of look back in hindsight and say, this is what my optimal policy should have been. So that's something we were able to solve for actually in closed form for some simple settings. And as you can see, it does better than our algorithm, but not always that much better. And again, it's not something you can solve for in practice. So again, the message of this is that we're able to learn policies that trade off between a higher communication cost and sending more valuable data. And we're even able to get close to the optimal, at least in some cases. So this particular point on the trade-off is very close to the optimal trade-off.
What happened to that point there that like looks around on the
this
dark blue? Yeah.
I don't know. I think this is just a reinforcement learning thing.
Okay.
Yeah.
Does the energy cost include the receiving signals from the?
Yes. Yeah. So it does include the cost of receiving signals. Yeah.
So this all depends on the starting point of the fire?
Yeah, that's a good question. So I think we looked at various starting points, and we were able to adapt to different starting points.
But I guess like each starting point will get a different project front or different.
Yes, so depending on the starting point, there will be a different shape to this.
Does it inform like sensor placement as well intuitively, right? I mean, you can also.
Yes, yeah, it could inform sensor placement. Yeah. So some of the related work we were actually looking at did look at the sensor placement problem. So we were trying to see, could you adapt that problem to this communication problem? it turns out it's not so straightforward. But intuitively, yeah, it should inform where you place the sensors.
So presumably the fire can destroy sensors, right? So just the processes, simulations, consider that form of sensing, or is that future work?
That is a good question. Yeah, so.
Right?
Yes.
Well, that's me.
Yeah. I actually don't remember whether we included that in the simulation. I think we did say that once the sensor has predicted that the fire is coming, it sort of shuts down. Now, of course, if our predictions are wrong, you know, you may get more noise in the system. So yeah, but that's something we should definitely consider in future work.
Is that sensor more useful? It's right next to fire. I don't know.
Potentially, right? I mean, if you've already predicted the fire is there, then maybe it's not so useful to confirm that. But yeah, so we're able to balance this trade-off. Okay, so yeah, just to recap, so we were looking at this constrained IoT sensing problem. We proposed a reinforcement learning-based solution to learn sort of when data is valuable, and therefore when sensors should communicate this data to kind of update our model. And we evaluated this on realistic wildfire propagation data. So this is my last slide. So again, I talked about two sort of very different seeming applications in this talk. But what I hope to do going forward is to look at other examples where, again, you have data collected by different sensors, you have constraints on how much these sensors or devices can communicate, and sort of try to develop new learning methods that respect these communication and privacy constraints, but still account for these correlations between the data that's being collected at different devices. Yeah, so these are some examples of things we're doing. So we've been looking at, can you use foundation models to kind of capture these sort of latent correlations and maybe save yourself the pain of having to learn these in an online manner? Are there any sort of general theoretical frameworks we could use to get sort of theoretical guarantees for how well these algorithms perform? Especially if you're trying to use like multi-agent reinforcement learning to decide which sensors get to communicate, it's very hard to get theoretical bounds on the performance of those sorts of algorithms. Yeah, so I think this is a very rich space. There's a lot of potential applications here. So these are just two examples of things that we've seen in my group, but I hope to investigate other examples in the future and help to sort of develop this in a more general way. All right, so let me end there. But thank you, everyone, and I'm happy to talk offline if you have other questions or comments. Questions? More questions for the speaker?
I wonder, have you formulated the privacy leakage for the report? Like, I'm asking it because I think for homomorphic encryption, it could be perfect secure. So the privacy leakage should only be in the online training state.
Yeah, so we didn't explicitly model privacy because, as you said, with homomorphic encryption, there is no privacy leakage. But I do think that's an interesting area to look at for the future.
I'm curious about something you said in the first part, where you said that the IID can cause instability or divergence of federated learning. So that surprises me, because I would think if every client just computes the gradient with respect to their data, and then the server just aggregates all of those with an appropriate step size, that's the full gradient, and when the right step size is converged. So I'm probably missing some subtlety there.
So what can happen in federated learning is usually you actually have multiple local iterations of stochastic gradient descent. Yeah, so you know, for a large number of iterations, you have divergence. Yeah.
I mean, you said non-IID is better or IID is better?
So with IID, you can, non-IID is worse in that sense, yeah, because you have more divergence between clients. But yeah, in the graph setting, non-ID could actually be better because you have fewer edges between clients.
So basically, for these applications, like, how do you think foundation models are useful? Because they are, given that they are large.
Yeah. So that is a good question. So we really just started thinking about this in our initial formulations. You have a foundation model sort of sitting at the coordinator. So it doesn't really matter how large it is because the coordinator has a lot of resources. Yeah, if you wanted to push this foundation model down to the clients, that is a very difficult problem. So we're still trying to figure out how that could work. Maybe you could do some sort of embedding, and then if the client has the embedding, then that can help it sort of take into account these correlations without having to learn the correlations itself. But yeah, again, we're not quite sure how that will work yet.
Great. Thank you guys for the great questions, and thank you, Carlee, for a great talk.
Yeah. Thank you.
Dinner, right? So yeah, I will see you.